Good morning, everybody. Before I start, I want to say I look around the room and I see a lot of familiar faces. Some of these faces are people that were mentored by Ramon, like myself, Fernando, Ruben, and others. And I just want to say how important Ramon was to us. Ramon once called me from Western Sahara simply to return the call because I had a concrete question. And he was in Western Sahara doing some type of consulting. He called me one time leaving Area 51 because he had some pavement issues in the top secret site. That's the type of person Ramon was. He was a mentor above all. He was an incredible engineer. He was an amazing human being. And a good portion of what I know with regards to repair of concrete, with regards to managing a business in general, with regards to being a good human being and a good person to others, I have from Ramon, from people like Pepe, and from those others like Ruben and Fernando and others around the room we've worked together for the past two or three decades. So the most important thing that I'd like you to take from this presentation, one, is the love and respect that we have for Ramon and what he meant to us and what he meant to the industry and to all Latin engineers. Now, with that said, I'd like to talk to you about a project that's dear to my heart. It's a project that took several years in the making, and it was the restoration and repair of the Capitol building dome in San Juan, Puerto Rico. The Capitol building and everything, as you've seen, is one way or the other tied to Ramon. Ramon actually consulted and did repair work years before we entered the project after Hurricane Maria. The Capitol Dome is one of our important heritage structures in Puerto Rico. It was built over 100 years ago, and it served as a state legislature for Puerto Rico for all that time. It's a very interesting building. It's pretty much a concrete structure. It might look like the Capitol building of the United States, but in reality, it wasn't modeled after the Capitol. It was modeled after the Library of Columbia University because it was the same architect that did it. It's a concrete dome, as we said, and it has Georgia white marble on the outside. And despite the project being a general contracting job that involved HVAC, new luminaries, electricity, waterproofing, which was a big portion, we will speak about two very important parts of the project that are most important when we talk about concrete and concrete repair. So anyways, as we said, we're going to be discussing very specific portions of that work, and we'll discuss initially existing conditions, then go a little bit about the structural system, and then talk about some of the solutions we came up with. Now, why did we rehabilitate the structure? The two most complicated or complex portions of the job were, one, the repair of the dome itself, the concrete dome. The concrete dome, it was discovered, Pepe Izquierdo was the designer. It was discovered that was extremely voided inside. It had a good portion of its space. It was voided space, large amounts of concrete segregation, and this had obviously impacted, the capacity of that dome to handle water and water filtration. There was ample issues of water filtration. The job in reality starts because on one end you're having terracotta pieces fall off the structure, and on the other end you're getting water into the Speaker of the House's office, for example. So with those things in mind, they started investigating the project and determined that there was huge issues with the cupola itself. In addition to that, there was large elements of concrete delamination and the terracotta facades, which we'll get into. So here's the dome exterior. Now, if you look at the dome, the bottom part of the dome, that's where the terracotta facade sits. It's a small portion of the entire facade, but it's a very prominent one. Okay, it extends in an overhang around the periphery of the dome itself, and then you have the dome structure, which on top of the dome rests the lantern of the legislature. And if you look at a cross section of the interior, you're going to notice something that you don't see on the outside. In reality, there are two domes. There's an exterior concrete dome. There's a space within it. And then there's a bottom interior dome. Now, if you ever walk into that structure and you see the beautiful paintings on the top, they're hung from that second level. You're not seeing the outside. You're not seeing the outside of the exterior. And thus, when water would come in, it would infiltrate. It eventually would trickle down and potentially hit the paintings that were there. And restoring the paintings, that was another separate job. So when you walked into that small space, here are some of the issues you would see. If you look at the dome from the interior, you'd see the large amount of segregation and voided spaces that you had. You had ample cracking, a lot of spalling, not that much corrosion on the outside. This is an example of where we see some exposed rebar. Look at the rebar. The rebar in reality isn't in that bad a shape on the dome. We're going to see in other elements of the structure that it was in a pretty bad shape. But in particular, the dome's issue wasn't an issue of corrosion. It was more an issue of the voided spaces that you had. It was pretty much a crackerjack. So as you went along, you would see also that there was ample evidence of cracks. In reality, these cracks were more spalls. There was a delamination, internal delamination. And when we started removing them, we would see that we really didn't have, a crack to inject into with epoxy. It was in reality spalls. And one of the photographs that you see here is us following that delamination around. This is the top of that dome, and these are the beams. These are the main girders that where the lantern rests. If you look at it, you're going to see that you see a lot of aggregate, and you see very little cement paste. That was one of the issues. And another interesting issue of it is the fact, if you look closely, you're also going to see angles, iron angles that were used as part of the reinforcement system, aside from rebar. Now, anecdotally, it's mentioned that these iron angles came from the railway industry 100 years back when Puerto Rico had rails. In these photographs, you're going to see a little bit closer. You're going to see the lack of cement paste on the photograph on the left. On the photograph on the right, you're going to see the condition of the stirrups. In many cases, you'd lost total cross-sectional area of the stirrups, so you had no shear capacity that you could, other than the concrete. So how do we go about fixing this? Well, initially, the plans called for a micro cement injection with 16-inch off-center ports, vertically and horizontally for the entire dome. And you could possibly think that's pretty much straightforward until you get to the job, because theoretically it might seem that you're going to inject on one port, you're going to see counterflow on the next, you're going to switch that port off, and you're going to keep on moving, and you're going to keep on filling the entire area. The reality is, as we'll see, that's not the way it worked. There were many unforeseens. There was the concrete segregation, but in the end, the main driver of the repair was micro cement injection. We used a rotor stator pump with low pressure, under 30 psi, and in the end, we ended up filling up about 8% of the total volume of the cupola itself. The material that we used was master rock by master builders. And here comes when we start doing the work. When we start doing the work and we start injecting, we start noticing that there are parts of the structure, parts of the concrete that start spalling off. Why? Because they were completely loose from the beginning. So you can't really just inject and be done with it. We had to rearrange our methodology, and we had to first identify all the loose spalls, remove them, and do a standard concrete repair, 90-degree angles, install mortars, a competent repair mortar. And once that was done, then we could come in and safely inject the entire dome. And when we started injecting, here come the additional problems. We started getting micro cement trickled down on the sides of the dome itself. So we had to place people on the outside to do observations while we were injecting, because this happened in multiple places around the windowsills, in the middle of joints, in the middle of the height of the dome itself. And that added an additional element of despair to our work when we were working. And obviously Pepe, who's smiling now, when we would go to those meetings, he wasn't smiling too much. Once that was finished, then we tended to the girders that support the lantern on the top. Now, you had seen in the beginning the photographs of the girders themselves. Very low cement paste. So it wasn't necessarily just an issue of coming in and repairing the concrete, cleaning out all the corrosion, and integrating corrosion inhibitors, and putting in a repair mortar. You had serious issues with the fact that you had very little cement paste. So you could repair in one portion, and possibly you're not looking at a bunch of other places in that beam that have exactly the same problem. And in the future, when it starts filtrating water again, water is going to trickle down and re-corrode the areas. So Pepe and I sat down, and we ended up deciding on a system where we also did microcement injection into all of those beams, just as we had done with the cupola. And in the end, to finish it off, since we had so much issues with cross-sectional area of the rebar, we added in additional shear reinforcement with carbon fiber laminates, just to make sure that we were compensated for that loss of reinforcement. So that being said, that's more the concrete repair portion. Here comes the terracotta facades. The terracotta facades for me were probably the biggest challenge. Okay, let's understand where this building sits. It sits right in front of the coastline. It'd be a perfect boutique hotel, if it weren't the legislature. Who knows? It might be better being a boutique hotel than the legislature. Yeah. So we have a tropical environment. We have high winds. We have the saltwater spray hitting constantly. And let's add to the fact that in Puerto Rico, maintenance is an issue. As opposed to when you have to go and change the oil in your car in Puerto Rico, typically they don't maintain their structures. So we had to deal with all these issues. And when we got close to the terracotta facades, we saw what was really happening. We were getting portions of those terracottas that were falling off. And when you looked inside of it, you could see that the supports were all corroded. And in addition to this, the entire facade, which is terracotta, and terracotta is supposed to not be voided. It's not supposed to be filled with concrete. Because the way it works is, if water goes in there, it trickles down and it drains. This terracotta facade, portions of it were filled with grout. Other portions were not filled with grout. Some of the joints were cementitious. Some of the joints have been repaired with elastomerics, not permitting the water to come out. So in the end, what you had is a very, very hybrid structural system, whose behavior was completely heterogeneous. These are some of the existing conditions. As we walked around the site, one of the things that was constant was this cracking and this rust jacking, where we would see these exposed angles, which were in reality the support system of the terracotta facades. When you look at the difference in the colors, those were repair intents in previous times, and when we got close to there, we saw that the joints had been covered with an elastomeric, which is a complete no-no when it comes to terracotta restoration. So once we opened up some of the areas that were so severely damaged that they needed to get removed, this is what we saw. We had a topping that had a mixture of clay brick with a cementitious topping. We had what they called in the plans a clinker, which was really a cementitious mixture with carbon. Then we had the concrete slab, and then you could see the angles that extended outward, and that served as the main support system for the terracotta facades. So talk about heterogeneous. All these materials, none of these has similar engineering properties. They're completely different. How do you estimate and how do you predict behavior when you have such a heterogeneous situation in your hands? So you have multiple joints causing issues. You have multiple locations where there's water ingress. You have corrosion and slab jacking, and you have the terracottas. So how do you deal with this? How do you deal with such a complex situation? The initial project called for specific repairs in different portions of the facade. The reality was that once we got up there, we saw that the entire support system of the facades was in bad shape. And I used the term imminent failure, and I meant it when I spoke to the government. They got upset at me because they said you could never say that word in front of the press. But that was the reality of what we were looking at. And we had two options: either figure out a way where we can reinforce the entire thing without having to remove it, or remove it and redo the entire structure, which would have cost millions and millions of dollars more than it actually did. So before we get into the engineering portion of how we did it, let's think a little bit about the load path. Let's think about how this structure was supported. We had angles at a level of the terracottas that were spaced at 18 inches, and they came out, they cantilevered out, and that's what supported the entire facade. You had a concrete fill behind it to serve as a counterweight, and this is actually a photograph of the plans, and it shows reinforcement inside the terracottas themselves. That never happened. When we started removing some of those terracottas, they didn't have any reinforcement on the inside. They were literally just sitting there with grout between them, and they had been built up, and it's a miracle that they hadn't fallen off with high winds or some of the movements that we get in Puerto Rico. So we knew we needed an alternate load path to be able to reinforce this. And we knew we had to figure out a way to not remove the entire facade. And the specifications called to consider seismic loads when doing the repair, to add a little bit of salt into the mix. We needed to think about system durability, the interaction of the multiple construction joints, and very importantly, corrosion mitigation in the end. So we came up with a system that is actually a system from Canada called the Syntec anchoring system. And the Syntec, the way the Syntec anchoring system works is you insert angles into discrete portions of the structure, and you anchor the structure in place without having to remove the structure. In the corners, where Syntec couldn't be used, we used a standard system with stainless steel angles to support the entire structure. Now, one of the particular things of the Syntec system is that it's an anchor that has a portion of it that has a grout sock. That grout sock gets inflated, it presses upon the surfaces of the sides of the substrate, and that's the way it makes the mechanical bond. It's perfect for weak substrates like this one. This is a sample of what we're talking about. On the left, you're going to see one of these ankles. In reality, it's either a bar or an HSS stainless steel tube, with a portion of it specifically designed for your substrate, for your particular situation, where you're going to inflate that grout sock with grout to perform the mechanical anchorage. And on the left side, you're going to see the grout sock inside a substrate, where it molds itself around whatever things it has around it to make that bond to the structure itself. So in the end, the final design had to consider not only the vertical loading, but also seismic loading as per the IBC 2018, which is the code that the Puerto Rico Building Code defers to in regards to seismic issues. And we ended up having to reinforce the entire periphery of the structure. If you see on the sketch on the right, we have multiple levels of anchoring. We have 2 levels of horizontal angles that would stick out, okay? And then we also had one at 45 degrees to help with the overturning of the pieces. Actually, 3 levels of anchoring plus the 45 degree. We also added in vertical anchors in very specific places to try to help and consolidate the structure and help it act as one as much as possible. On the corners, as we had discussed, we ended up using a system of stainless steel angles to sit all the new terracotta pieces on top, so that because the system was very difficult to get the Syntec system to work at angles in those corners. So in comes execution of the work. As with the case with the dome itself, here we need to understand the level of sensitivity that this project has. The reality is most of the structure was being supported by corroded angles that with a flick of a finger you could break. So the structure in itself throughout time had probably redistributed its forces to maintain equilibrium. So we had to be mindful of this when we did the work. So initially we had to shore a portion of the structure before we started working, and we would remove then the modillions. The modillions was one of the terracotta pieces that you see in the second photograph. We would cut it at the base so that we could expose the iron angle behind it. We then would remove that iron angle so that in the future it would not cause additional rust jacking, install the Syntec anchors, and then reinstall the modillions, and then resurface the terracotta facade. This is some of the work that was being done. We drilled at multiple levels, and when you see to your right, what you see is the anchors themselves, and those tubes are the tubes where you fill with grout the anchor itself. So you would install multiple anchors first, and then you'd come back and grout them in. These are some more photographs of the ones on the top there are the ones that are at an angle that were driven into the concrete substrate, and you had a peripheral beam, a peripheral girder around that you could use, and we would drill into that girder so that you had a competent substrate driven into it. And when you see the photograph in the middle, that's what the anchor would look like inside a terracotta element. The grout sock would inflate to the level where it would hit the walls, and it would hit the top and bottom portion and sustain it in place. These are some of the works that we did on the corners, where we had to extend the stainless steel angles and anchor them in and create a beam, a reaction beam behind it, so they would be well supported. And in the end, what did we learn? What did we learn? First, with regards to the terracotta facade, the major problem was the rust jacking. You didn't have an adequate support system for it. There was a lack of a competent waterproofing, and I didn't discuss the waterproofing, but that was a big portion of the job to make sure that water would not come back into this place. And the Syntec anchors were the reason why we were able not to have to completely remove the terracotta facade and redo it. With regards to the dome, the microcement injection restored the integrity of the entire dome. Like I said, literally it was like a cracker jack before it was re-injected. It's going to protect against future water ingress, and the carbon fiber has helped us enhance not only ductility, but enhance and compensate for that loss of cross-sectional area. So in the end, I'd just like to leave you with this. Thank you, Ramon, for being such a great mentor to all of us, and you're a legend to us, and you will be remembered for the remainder of our professional lives. Thank you.